Throughout the semester, we've covered topics such as static electricity, electric fields, and magnetic fields. We also engaged in many discussions with each other through Canvas. Some of those discussions have covered topics such as string theory and our own definition of physics. Many of the discussions were about education in America, and I've realized through these discussions that there are a lot of problems in our education system and that there isn't going to be an easy fix. Not a fix like a one-size-fits-all type that you tend to hear about, but one that involves many solutions. We also researched many different neat resources. The ones that I liked the best were probably the rip-rap machines because I thought it was pretty cool that you're talking about a 3D printer that could basically build. The other neat resource that I liked the most was the Faraday cages and music Tesla coils, which I also found very interesting. I thought it was pretty cool that I found some instructions on how to build a Tesla coil that could be controlled by something like Arduino. Static electricity was the first topic that we covered in class, and we used the sticky tape lab to kind of demonstrate some of the things that went on with static electricity. We learned about Coulomb's law, which is basically this force between two charges. This is also where David taught us about derivation, where we basically can use something like the units that we're working with to work through the math. This is much simpler than using just numbers, which can get pretty confusing when you're going from this to something like this. And I've actually started using derivation in some of my other classes, especially my circuits class, where you're looking at circuits with inductors and capacitors and multiple resistors. It certainly simplifies the math a good bit. We also learned about induction and triboelectric charging, which triboelectric charging is basically where you can get an insulator to have a charge through friction, like rubbing a balloon on your head against your hair, where charges from your hair are basically transferred over to the balloon. Induction can cause polarization, and basically what happens there is that a charged object in close proximity to another object will basically cause the like charges in the neutral object to move further away, and this causes an attraction between the two objects. After static electricity, we started working with electric fields and energy and potential and electrical forces. But first, David actually kind of showed us how electrical and gravitational are very similar. And what he did was kind of make this chart, and we actually see how many of the formulas between gravitational, or whether we're talking point particle or uniform field, are actually very similar to the electrical formulas. With gravitational, we were looking at mass, as you can see by all the formulas here, and in electrical, we're actually looking at the charges. We learned that charges actually produce an electric field, and that the electric field produced by a positive charge will actually push other charges away, well, like charges anyways, and that negative charges will actually pull charges to them. One of the tools we began using at this point were the FET simulations that's produced by the University of Colorado. And what we see here are, a positive charge right here and a negative charge here, and these arrows represent the electric field lines. These circles are actually equipotential lines, and they're similar to a contour line on a map. Basically, we're on a map. The contour line, every point on this line is at the same elevation, and they have the same potential gravitational energy. For here, this is the same potential electrical energy, and that the equipotential lines and the electric field lines when they cross are actually perpendicular to each other. As we can see that the electric field lines from the positive charge are going away from it. Meanwhile, the field lines are actually going towards the negative charge. We also began learning about current and potential difference. In doing this, we worked with a capacitor with batteries hooked up to it, and we were basically measuring voltage at different points. We were looking at voltage between the terminals and the voltage from which was the potential difference, and we were also looking at the potential difference between one end of a wire and its other end. And in this situation, that the wires actually kind of work as equipotential lines, and so that the potential difference between here and here is zero, or actually very close to it. But the potential difference between here and here is pretty much the same as the potential difference between the two terminals of the capacitor. During this, we looked at this was hooked up to a Logger Pro, and we were able to basically time the discharge of the capacitor. And this shows basically where we had a little more than 3.5 volts potential difference on the capacitor, and then it discharged in about 0.2 seconds, something like that. But with this, we're basically looking at, that there was a electrical field between the terminals, that if B was a terminal and C down here was the end of the wire that was connected to that terminal, that there was an electric field between them, but there was between the two terminals and between the two wires. We also learned how the potential difference in a circuit is what causes charges to flow through that circuit. And charges that are flowing through the circuit is actually what we refer to current, which is often represented by the letter I, and the unit for current is amp, which is coulombs per second, or charges per second. And we also learned about Ohm's law, which is the current is equal to the voltage divided by the resistance. One of the things David taught us about resistance was that at a particle level, that resistance is caused by particles that interfere with the flow of the charges. And we also use this traffic jam analogy as well, where from here to here there wouldn't be any resistance, but right here all of a sudden you're seeing resistance, basically where you're seeing a 4-lane road get cut down to 1 lane. After this, we began working on Project 3, which was where we were building a coil gun from the flash circuit of a disposable camera. And the flash circuit contains a transformer that basically takes the low voltage of a battery, goes through one inductor that then induces a current in another inductor that boosts the voltage up. and charges this capacitor. And disposable camera flash is about 350 volts. So it's actually a pretty good boost from the 1.5 volt battery. But the main purpose of the coil gun was to kind of introduce us to magnetism, because as current flows through this coil, it generates a magnetic field that would attract a BB that would then be moved through this tube and shot out the end of it. We had a competition, but my coil gun didn't quite work well. I don't think I had the BB close enough to the coil that for it to get attracted by the magnetic field. But one of the things we began learning about magnetic fields was that magnetic fields are generated by moving charges. How we determined that magnetic fields were generated by moving charges was simply placing a wire over a compass. And here there's no current flowing through the wire, and so it's lined up with the compass needle. But once we produced a current through the wire, then we can see that the needle's moved, and so that and that's because of the magnetic field is affecting the compass needle. Throughout the semester, we've worked on several projects, and I've already discussed project 3, which was the coil gun. The other 3 projects was first project. Me and Trey worked on a number of the Arduino projects that were in the book. Some of them were just merely lighting an LED. The one we presented on was the crystal ball, where we used a tilt sensor to change the display of an LCD. And here's a quick video of that, and we can see all of this is done through the programming code for the Arduino microcontroller. And but that was project 1. That was ended with that, but we worked on a number of the projects out of the book. Project 2 was a little bit more detailed. With project 2, we were able to use an ultrasonic sensor to track the motion of an object being moved back and forth. And basically what happened was the Arduino would take the data it collected from the ultrasonic sensor and send it back to the laptop. And then that data was then imported into VPython, and as we moved the object back and forth, the object in VPython would move back and forth as well. And we had some issues with it. It didn't always want to work as smoothly as we wanted to, but we did get it to work where it was moving objects back and forth. From here, our last project was project 4, and me, Christian, Nika, and Trey decided to build this ShotBot. And basically we had to buy the pumps. We had David print these 4 platforms, and basically by pushing a button, it would the Geekduino board, which is shown right here, would activate this pump, and it would pump for about 3.2 seconds to fill up a shot glass. Here's some other views. And here's a video of it completed. One of the things that we wanted to do was to, instead of using a button for both of them, was to use a light-dependent resistor as kind of a sensor to make it an automatic thing. So this was project 4. And that's about it for the semester. Thank you.